We've got this example right here we've been looking at. I can't find my page. Here it is. So as point Q approaches point P, as it becomes infinitely close, the slope of the secant line PQ approaches, say it louder, the slope of the tangent line. You want to understand that phrase well enough so that if you were asked to reproduce it on the test, maybe not verbatim, but you could say something about the slope of the secant line approaching the slope of the tangent line as Q moves closer to P. You should be able to think of the type of drawing that we're doing here. This should be conceptually in your mind. Now, we spent a lot of time on the algebra. This is the graphical representation of what we've seen. So we'll get to the definition of a limit here later, but right now we flip it over. Let's go to this example, okay? Because this kind of slope of the tangent line has a lot of application, and we're going to look at just some basic application here. Your first example talks about an object being dropped, and it has a certain placement at a certain time, okay? So what is the force that's acting on an object when I drop it? Gravity is working on the object, okay? So we got gravity going on here, and it says it falls, the position is modeled by 4.9 t squared. So what I can do is I can look at it at one position and then look at another position and be able to calculate its velocity. For example, if I leave here, okay, and I drive to Owatonna, and let's suppose that Owatonna is 30 miles away, and it takes me 1 hour to get there. What is my average speed? 30 miles an hour. You take my distance I've traveled, and you divide it by the time. You get that 30 miles an hour. Suppose I traveled 30 miles in half an hour. What is my average speed? Because 30 divided by 1/2 is 60. So we have the same type of thing here. Average velocity is that speed. So it says find the average velocity for the time period beginning with time 3. So we're looking from time 3, and then we're going 1 second further. So if we start at time 3 and we go 1 second further, what's our end time? 4, okay? Now I have the time. I now need the position of the object. I'm going to take out my calculator, and I'm going to go to y equals, and I got 4.9x squared. I type in my two values, 3 and 4, and I get 78.4, I get 44.1, okay? So there we have it. Now I'm going to do my y sub 2 minus y sub 1, which is 34.3 divided by 1. And I get 34.3, and I'm going to need a label here, okay? What are these? What are the y values measured in? What's the unit of measurement for these? Meters. Very good. Question. Y sub 2 minus y sub 1. Yep, I put the 4.9 t squared in my calculator. So you are going to do the same thing, but instead of choosing 3 and 4, we start at 3, and if we go 0.5 seconds, what's going to be our end time? 3.5. So I would like this group over here, okay? Actually, we'll do the two outside groups, okay? So Aaliyah's group and Rachel's group, you guys are going to do this one. Come up with the y values and come up with the slope. This middle group right here, you guys are going to do 3 to 3.1. Come up with the y values and the slope. This group right here, Callan's group, you guys are going to come up with the y values and the slope, okay? When you come up with the slope and the y values, verify them with somebody else so you can make sure that you're doing it correctly. 3, we're trying to center on just one value of 3. So instead of average, meaning 2 values, we're looking for instantaneous. find the instantaneous velocity at exactly time 3. We can see these values are trending down towards. If you were going to pick a value that you feel like it's trending towards, what would you choose? Maybe 29. 29 would be a reasonable guess. I've worked this problem out before. If we were to choose, instead of 3.01, how could we come even closer? We could choose 3.0001. If you do that, you're going to find that actually 29.4 meters per second happens to be what we would say the instantaneous velocity. Now, Michael, if I asked you to make a guess according to these values, you said 29, I would mark that correct. Okay? But if you wanted to get even further and closer, you want to make sure that you do that. Okay? So, we're not typing in the right values. I'll come help you in a second, okay? Let's move on to this one. I'll help you figure that out, okay? All right, now we're not given a function. We're given a table, okay? So we don't have an equation. We're given table values. Number of bacteria in a dish or your cell phone is modeled by the given data, okay? So at time 1, you have 5 bacteria. At time 4, you have 8. And at time 20, you have 115 bacteria, okay? Things are getting a little bit out of control. Bad day, right? Got to wash those hands. It says find the average rate of growth of the bacteria at time 1 and lasting 19 minutes. So at time 1, how many bacteria are there? 5. 19 minutes later, what time is it? It's 20. How many bacteria are there now? 115. So average means I use 2 points. 2 points. Instantaneous is 1 point. That's part of what makes calculus challenging. You have to start to understand the language. And average and instantaneous is crucial that you would understand those pieces. So let's look at this. If I want to find the average, I'm going to take 115 minus 5 and divide it by 20 minus 1. And what do I get? 5.7 bacteria per minute, right? Okay, so Dylan and Calvin's group, you guys do number 2. Emu's group, you guys do number 3. And Alex, your guys' group do number 4. Okay, go. Divided by the x value. That should be 0.5. So you're doing y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. Got it? Okay. Good question. Yeah. Hi. Just ask that question. Keep asking us questions. So you got this 19. What do you got?
Oh, I did that backwards. The number of factory I got messed up with like minutes. Yeah, that's why mine.
What do you guys got? Jake, I gotta hear you.
9/7. I don't.
9/7. So you got 1.28 bacteria per minute. Okay, what do you guys got? Okay, so we see some trending. It says use a graph of the data in order to estimate the instantaneous. So if it says instantaneous, how many points do I want? Yeah, if it says instantaneous, I just want 1 point. So what I'm going to do is I'm going to make a graph here and see if we can come up with a visual representation and be able to use actually some of our data in order to come up with this. Now, part of what you guys do not know that I know is these problems I've added from previous times of looking at the AP exam. So these are excellent problems that you could possibly see on the AP exam, which is why I built them in. That's why we're not doing just the algebra, okay? So here's what we got. I'm going to make a little graph here, and I'm going to put bacteria over here. I'm going to put minutes over here. I go up to how many minutes? 20. So I'm going to go 20 minutes there. I got 10, 5, and 15. And then I go up to about 120 bacteria. I'm going to plot my data. What's my first data point? I'm sorry, we're going to look at this data right here. Okay, 1, 5, yep. So 1 minute, 5 bacteria. What's the next one? 4, 8. Thank you, Rachel. What's the next one? 8 and 14. 1332, so I'm going to go up a little bit higher. Anybody recall some of our work last year? What type of a graph would you call this? Exponential, very good. We're talking about growth. Maybe exponential has to do with, say e to the x, something like that. Okay. So it says we're trying to find instantaneous growth. So important that you see this through, that you understand conceptually what we're going on. Instantaneous means how many points? At what time? T equals 8. So I'm going to look at this guy right there. Can anybody think of a way that I could approximate the slope of that line? What? Doing what we've been doing. The problem is before we had an equation. You don't have an equation now. We can't type in like 8.1 and 8.01, can we? We have no options. It's in front of you. Look at the graph. Don't think about an equation. Look at the graph. Okay, good. We can use 814 as a point on the line. Could you connect two dots together that look like they represent about this slope? Yeah, the one behind it and the one in front of it, right? Like if I connect these 2 points, we're just trying to come up with, does that look like it would be about a good estimation? I think it's a great estimation. Let's choose the one in front of it and the one after it. So what's the one in front of it? 4.8. What's the one after it? So choosing the one before and the one after would hopefully give a good representation of that. I think that's a great idea. Let's try that. So 32 minus 8 divided by 13 minus 4. And I get 24 over 9er, which is 2.67 bacteria per minute. So we found a lot of examples of average growth of bacteria, but we would estimate that the instantaneous rate of change is 2.67. So you can see that we were given equations. You guys have learned how to deal with equations. Here we were given tables. You learn how to do with tables. Now let's actually go to the graph. This last one, use the graph below to draw a line tangent to the function at the given point. Then determine the equation for the line. We want to do x is equal to 0.75. Can somebody, well, 0.75 is going to be right about here, right? So I'm going to mark that spot on the graph as right about there. What do I want to draw now? A tangent line. You okay with that? Does that look reasonable? It's not great, but would you say it's reasonable? My goal is to now write an equation. What do I need in order to write an equation for this line? I need a point. Well, estimate that point. Estimate it. What's the x value? What would you say is the y value? Sure, maybe 0.9, 0.85, something like that. Sounds like a great idea. What else do I have to find? How about slope? How are you going to do it? How about we just pick another point? So how about we go from 0.75, 0.9, and we go over to 0.4. Does that sound reasonable? Yeah, you're exactly right. The line is not just great, but it is an estimation. We're just going for an estimation here. So how do I calculate this? Can I use this to calculate slope? Yeah. We've got 0.4 minus 0.9 over 0 minus 0.75. So we get 0.5, negative 0.5 divided by negative 0.75. Anybody do that for me? What? 2/3. So we've got, so slope is 2/3. So I have y equals 2/3 x. And here's what's cool. Did I already pick out what the y-intercept was? Yeah, I already picked out 0.4. I was trying to help myself. I'll write it as 2/5. So we should be able to look at a graph, be able to, estimate a tangent line. We should be able to look at data and try to come up with an estimation for a tangent line. And we should be able to do it using an equation. You did the equation on the first 6 problems on your worksheet. Your assignment now is to finish off the worksheet. These problems will follow basically identical to what we did for examples 5 and 6. Whoop, 5 and 3. Interesting. Okay. Very good. Yep. So you should have some data to follow, and it shouldn't take you very long at all, probably about 5 to 10 minutes. Come back tomorrow. Tomorrow we introduce limits, okay? A strong introduction to limits. And tomorrow the mathematics will seem a little bit more normal, I guess.